Welcome to Snacks Weekly on Data Science. This podcast is all about making data science and machine learning knowledge accessible and less intimidating. Today, we are talking about forecasting. This episode is based on a tech blog titled Real-Time Spatial-Temporal Forecasting at Lyft, written by their engineering team. You can find the link in this episode's description. Throughout this episode, we will explore this topic from both the business and data science angles. Now, let's dive in. On the business side, let's take a look at the problem to be solved. Lyft is one of the leading ride-hailing platforms. It operates across hundreds of cities in North America. In such a fast-moving, high-dynamic marketplace, both supply, which is available drivers, and demand, which is ride requests, they can change quickly across time and location. For Lyft, the company, being able to anticipate demand and supply at a very fine level of detail is very important. For example, predicting how many rides will likely be needed in a specific neighborhood in the next few minutes. These forecasts power real-time operational decisions. Dynamic pricing helps balance undersupplied regimes. Driver incentives encourage drivers to move into high-demand zones. And marketplace balancing ensures riders find drivers quickly. Without these accurate minute-by-minute, block-by-block forecasts, Lyft risks major inefficiencies. Longer waiting times, more idle drivers, miscalibrated surging prices, and generally poor matching experience between riders and drivers. That is the reason why the team invests heavily in real-time spatial-temporal forecasting. Spatial-temporal simply means predicting how something changes across both space and time. At Lyft, the spatial dimension corresponds to GeoHash6 cells, which is a small rectangular grid unit roughly 1.2 kilometers to 0.6 kilometers size. The United States alone contains about 30 million of these cells. The temporal dimension means generating predictions every 5 minutes, continuously. Putting these two numbers together, and you get an extremely high-scale forecasting problem. Millions of spatial units, each updated almost every few minutes. All of those tied to the business that depends on split-second accuracy. It's no surprise that this is a very challenging system to build, maintain, and improve upon. Now that we've understood the business problem, let's shift gear and dive into the technical side, specifically how the team approached this forecasting challenge. The difficulty comes from two main factors. First, the dimensionality and frequency are enormous. Predicting demand and supply for millions of spatial cells every few minutes is computationally intense. Large deep learning models could, in theory, capture complex patterns, but running them in real time at this scale may be too slow or too expensive. The second challenge is that the data itself is noisy, sparse, and spiky at fine resolution. Many cells have zero demand most of the time, and then suddenly experience huge spikes. Like after a concert or sports game, modeling that kind of volatility reliably is extremely challenging. Given both challenges, the team explored two families of models for real-time spatial-temporal forecasting. One is classical time series models, and one is deep neural networks. On the classical side of approach, the team experimented with approaches like autoregression or ARIMA, which predict future values based on past observations. Because spatial data involves many correlated time series, it is basically one for every geohash. The team considered either using one global model across all regions or grouping regions into clusters with similar historical patterns and training partition-specific models. They also evaluated spatial-temporal covariance models, which estimate correlations across both time and geography, as well as dimension reduction techniques like PCA and SVD. These methods compresses thousands of correlated time series into a handful of components, run forecasts on those components, and then project the results back to the geohash level. After looking at the classical side, let's take a look at the deep learning side. From the deep learning angle, the team evaluated models commonly used for spatial-temporal tasks. Recurrent neural networks, especially LSTMs, capture temporal dependencies by retaining information over time. Another one is convolutional neural networks, originally designed for images, can treat each spatial map as an image, making them useful for learning spatial patterns. After looking into both model families, each of those brings strengths but also trade-offs, especially once the latency, cost, and real-time constraints enter the picture. When the team compared these models, the results revealed a consistent theme. Model choice is ultimately a balance between forecasting accuracy and engineering cost. From an accuracy standpoint, deep neural networks generally performed better than classical time series models, at least when latency wasn't a factor. In offline experiments, where both models were retrained at the same frequency, deep neural networks captured richer spatial and temporal patterns. But as the retraining cadence increased, from daily to hourly to even few minutes, the accuracy gap narrowed. And at a very high frequency, the classical models could even outperform deep learning models. This picture shifted further once the real-time constraint came into play. Time series models can be retrained every few minutes, while deep neural network, because of their size and GPU requirements, usually can't do that. In Lyft's marketplace, short-term signals like what's happening in the next 5 to 30 minutes tends to follow strong autocorrelation patterns. That makes simple, frequently updated models surprisingly effective, especially during sudden spikes like post-event traffic. A fast refitted autoregression model adapts quickly, while a deep neural network that hasn't been retrained may miss rapidly shifting spatial dynamics. On the other side, for a longer horizon, if we look at forecasts beyond 30 to 45 minutes, deep neural network begins to shine. They capture broader spatial relationships, seasonality, and longer-term trends that classical models struggled with. Performance also varies by signal type and geography. Supply is smoother and easier to model than volatile rider demands, and cities with complex terrain weakened spatial correlations, making lightweight classical models more reliable. From an engineering cost perspective, real-time spatial-temporal forecasting requires enormous memory, fast data pipelines, and ultra-low latency inference. Stability and cost matter just as much as raw accuracy. Meanwhile, deep learning models are undeniably more expensive. They require GPUs, which can be 100 costlier than training classic models. And their inference load is heavier, and they demand more operational overhead to keep stable in production. Time series models, in contrast, are lightweight, inexpensive, and easy to refit frequently. They scale naturally across millions of spatial units without massive compute, and their results are far easier to interpret. With all these comparisons discussed, in real-world applications, businesses often prioritize simpler models with greater interpretability, lower inference latency, easier retraining, and importantly, lower total cost of ownership. These factors are essential when choosing cost-effective and maintainable solutions. Now, we've discussed both the business problem and the technical solution. Let's wrap it up. In this episode, we explored how Lyft identified the right algorithmic approach for building a real-time spatial-temporal forecasting system. Their study highlights the balance between accuracy and practicality and serves as a useful guide for choosing machine learning solutions that truly meet business needs. If you like the content of this episode, please subscribe to the channel. Give me a 5-star review and leave a comment. Your feedback is very appreciated, and I'll see you next week.